Welcome to the solutions to homework set number 4 for ECE 321 Analog Electronics. The first problem looks at an analog computer. With analog computers, you can implement pretty much any differential equation. In this case, I want to implement a third-order differential equation. The trick to do that is you create a dummy variable x that's just 1 over the denominator polynomial times the input, and the numerator polynomial is that times x gives you y. Now solve for x. Solve for the highest derivative. I get s cubed x, which would be actually right here. So what you get is s cubed x is equal to minus 7s squared x minus 2sx minus 20x plus u. So I can build that. I'll just have an integrator of 1 over s. Take s cubed x, integrate 3 times. So here's second integration, third integration. I can make up s cubed x as the sum of all those terms. So u is times 1. This is s squared x, sx, and x. S squared x gets multiplied by minus 7. Sx is minus 2. And x is times minus 20. So that's the block diagram way to represent it. In terms of analog computers, an integrator is this symbol, and I want the gains to be negative. So this would be 1 minus 20, and kind of like this is sort of s squared x, sx, and x. Minus 20 times x, minus 2 times sx, minus 7 times s squared x. Integrate 3 times, then the output is 10 times sx plus 15 times x. I now want to make everything negative, so around this loop the gain should be minus 7, and that's okay. Around this loop, the gain should be minus 2, so there's a minus, minus. I need to add this third op amp to make it a negative gain. Around this loop, the gain should be minus 20, and there's an odd number of op amps, that's okay. Then for the plus gains, I want the gain from u to y to be plus for sx, so here's 1, 2, 3, 4 op amps. 4 negatives gives you plus, that's why I added this op amp. And 15 for x, so here's 1, 2, 3, 4. Okay, so that works. You wind up with this analog computer diagram. And when I throw in the minus signs, those aren't x, sx, s squared x. There might be a minus sign in there. Now convert that to an op amp circuit. Each of these is an integrator. That's what this is. Have a capacitor in the feedback loop, you have an integrator. Here's another integrator. This is an amplifier. And the gain is the gains for the analog computer. For example, this guy right here has 4 inputs, gains of minus 1, minus 20, minus 2, minus 7. You get the minus free of charge. These are inverting amplifiers. U has a gain of minus 1, so 1 over RC is 1. This guy right here, minus x, has a gain of minus 20. So that'd be, where does that come from? Right here, that'd be 50k. 50k there. This has a gain of minus 2, 500k. And this has a gain of 7. So I took the resistor from here and actually drew it up here. So 1 over RC is 7. This has a gain of 1. 1 over RC is 1. Gain of 1. Gain of 1. Gain of 1. Gain of 10. Make that a 1 meg and 10k. And a gain of 15. 1 meg, 67k. So this is the circuit to implement that differential equation. That's the beauty of analog computers. You can do any differential equation. Annoying thing about them is it takes a lot of op amps, but it's one way to do it. Problem 2. This is you get to pick your own filter. The one I chose is I want to build a low-pass filter, basically a subwoofer. I want to pass frequencies out to 250 Hertz and reject frequencies about 500 Hertz. So below 250, I want the gain to be above 0.9 and less than 1.1. Above 500, I want the gain to be less than 0.2. And it's kind of your choice what you choose. Don't choose something like I want the gain to be less than 1.1 because a wire does that. That's too easy. But don't make it impossible for yourself, so you need a 50th order filter. This is what I chose, and it actually works out pretty well. So I want to come up with some filter where the gain versus frequency does something kind of like this. It's in this region for frequencies less than 250, below 0.2 for frequencies above 500. Don't really care between 250 and 500. That's problem 2. Give me the requirements. Requirements are all important. They drive the design. Problem 3. Given those requirements, give me a filter that meets them. First, I have to figure out how many poles I need. If I have a single pole, the gain drops by a half as frequencies goes up by 2. 2 poles drops by half squared, 3 poles half cubed, and so on. So how many poles do I need so the gain drops by down to 20% as I double the frequency? Solving, I get 2.32 poles. I can't do a fraction of a pole, so let's make it 3. Next, choose your type of filter. Butterworth, Chebyshev, elliptic, but pick one that you can build. I can build a third order Chebyshev filter, not too hard, so let's go with the Chebyshev. And from the lecture notes, corner at 1 radian per second is this. If I want the corner to be 238 Hertz, again, that's just kind of a guess, I'll scale all these times 238 times 2 pi. So 0.85 goes to 1275, 1.21 goes to 1.875, angle stays the same. And K is whatever it takes to make the DC gain 1. And MATLAB, I can sit there and see, does this filter meet my specs? So I'm going to go between 0 and 1000 Hertz. Omega is 2 pi f. S is j omega. Here's my first pole. Corner's at 1500 radians per second. Second pole, third pole is a conjugate of the second one. There's your G of S. And plot frequency versus gain. And I also mark gain of 0.9 at 250 and 0.2 at 500. What that looks like is this. At 250 Hertz, the gain is above 0.9, that's good. At 500 Hertz, it's below 0.2, that's good. So this one meets the specs. And actually took a couple guesses of where to put the corner. 1000 radians per second, 2000, 1500. 1500 works, so that's the one I showed here. So that's my transfer function. That works. To build the circuit, I need to come up with R's and C's. The first stage, one of our RC is 1275. So I picked R would tend to be 10K, 100K, 100K. One of our RC is 1275. Solve for C, and I get 78 nanofards. On the second stage, one of our RC is 1815. Pick R to be 100K, solve for C, C is 5.5 nanofards. And to find the gain. Gain sets the angle. I want the angle to be 69 degrees. Solving for K, K is 2.3, so that's 130K. So this circuit should implement my filter. Now check in Circuit Lab. In Circuit Lab, let's go there. I can build the circuit, and if I go under frequency domain, I can say I want to sweep V1. I'm going to start at 100 Hertz, go to 1000 Hertz, and let's have 100 points per decade, not that many decades. And we'll look at V2. So if I say, look at V2, this is the default. Phase, I don't care about. And dB, most people use dB. I don't like dB, I prefer magnitude. Kind of your choice. Do a sweep. And here's what it looks like. Let's narrow the range. And now what I can do is sit there and see what is the gain at 250 hertz. Here's 208, 234, 245, 250 hertz. Gain is 2.17. Again, that's relative to DC. DC gain is 2.3. That's K. So if I take, where is it? 2.177 over 2.3. The gain is 94% of the DC gain. The gain should be at least 0.9, so that works. If I go out to 500 hertz, where are you? 330. It'll be over here. This is in the way. At 500 hertz, there it is. Gain is 0.355. That's relative to DC. DC is 2.3, so dividing by DC, and I get a weird number. Something's wrong with my calculator. Let's see. 0.355 divided by 2.3 is 0.154, which is less than 0.2. That works. That's one way to do it. Second way, this is actually what you do in lab, is I would apply a sine wave to the input. So make the input a 250 hertz sine wave, measure the voltage at the input, measure the voltage at the output. In this case, the unit's going to be peak. V1 is a 1 volt peak sine wave. If I run this, or in lab, I can sit there and get the output, measure the output voltage. On the oscilloscope, I'd get the peak voltage. If you use a multimeter, I'd get the RMS voltage. As long as you're consistent, either one works. So that's 2.12. That's the gain. DC gain is 2.3. So relative to DC, it's 92%. Likewise, I could repeat at 500 hertz and maybe two other points, 100 hertz and 1000 hertz. That's kind of how you measure the gain in lab. Apply a sine wave. Sine waves are nice because those I can measure. If you have something other than a sine wave, it gets really hard. The last problem is build it in hardware. So here's what my circuit looks like. This is from the previous lectures. Here's your 2.5 volt reference. This is I think a times 11 amplifier, just to take my cell phone, amplify the signal so I can hear it. Here's my low-pass filter. Should be 3 capacitors for a third order Butterworth or Chebyshev low-pass filter. That output then goes to my push-pull amplifier that drives my speaker. To measure the gain versus frequency, again I'd apply a sine wave as an input. Sine waves I can measure. So make it 100 hertz, 250 hertz, 500 hertz, 1000 hertz sine wave, measure those 4 points. And then I can sit there and see, does my circuit match with what I calculated, with what I measured in Circuit Lab? The fun part is, once all that works, input an audio signal. And this should be a bass boost, so only the bass gets through. And we'll do that in just a little bit. But that's kind of what homework set number 4 is like for ECE 321, analog electric validation. Build it. So here's a circuit from week 1. That's my 2.5 volt source, my amplifier times 4. Here's the push-pull amplifier. It's really just a push amplifier. Here's my filter. So that's my third order Chebyshev low-pass filter, I think. It's supposed to be. So here's testing out the filter. Here I've got a sine wave coming in. And this is going directly from the first stage to the push-pull. Running through the filter, it's blocking 800 hertz, going down to 400, 200, 100, And at 100 Hertz, this is the output of the filter, input of the filter. Basically the same, a little bit louder because the filter adds a little bit of gain at DC. At the corner, it's 250 Hertz with a filter, without a filter, and 500 Hertz. After the filter, without the filter, with a filter, without a filter. If we put that on a voltmeter, you can actually get some numbers. And the more fun part is, let's turn that off. Play music through it. And this is without a filter. With a filter. With a filter. Without. With a filter. Okay, so that's products.